So hello everyone, my name is Karan and I'll be presenting this work which is property inference attacks on fully connected neural networks using permutation invariant representations. That's quite a mouthful. So basically what it is that we are launching a particular kind of privacy attack, property inference attacks on fully connected neural networks, which hasn't been done before, using a particular method called we're leveraging permutation invariant representations, which I'll explain in a while. So Chi, Wei, Carl, and Nikita were the authors on this as well, and they're here, and it wouldn't be possible without them. Okay, so this is a slide you've all probably seen a lot of times. Machine learning is popular. It's not even becoming popular at this time. It's already very deeply embedded in a lot of core crucial features that are out there, and in a lot of future endeavors that we are gearing towards as well, such as voice-operated personal assistance, face recognition systems, recommendation and ad targeting systems, autonomous driving, malware detection. We just saw memory forensics application using machine learning, deep learning. So, but training machine learning models by yourself is not particularly easy, and they require significant investment in terms of both computational resources and human efforts to tune and optimize them. So there is a market out there for model producers to come out and share machine learning models for both for free or for some kind of payment. And these could be either in white box form, where you release your parameters as well, or in black box, where you only release an API which allows you to ask for predictions. But as we all know in security, sharing is leaking information. So the model producer, in sharing the machine learning model, risks an attacker being able to infer private or confidential information about the training data set itself. And depending on the context, this could be actually pretty privacy sensitive stuff. So this has been, many attacks of this kind have been shown previously. There has been membership inference, where you can infer if a particular data record was present in the training data set. So the authors, for example, were able to infer if particular profiles were present in hospital discharge data sets using a model that was trained on that. So that is something that could be possibly very sensitive. There is model inversion, where you basically infer missing attributes of a data record. This kind of the authors were able to basically obtain the faces of people that they knew just the names from just the models that were trained to predict from basically facial recognition models. But the specific attack that we are interested in is called property inference. So what is the property inference attack? This attack basically asks and tries to answer the question that, given a white box ML model, where basically you know the parameters of the model, can the model consumer or attacker infer any global properties of the training dataset that the model producer did not intend to share? Now, what are global properties of a training dataset? So some examples are the sort of data distribution that the training dataset has, some sort of skew towards any particular attribute, or the environment in which a particular dataset was produced. And these affect the data in particular ways, which we can infer from the model. So let's take an example. So let's look at this neural network. It's basically a smile detector, which looks at the images of faces of people, and predicts if the person in the image is smiling or not. It's a simple binary prediction. Now, what kind of global properties could we infer from such a data set? So we talked about distribution skews. So for example, this data set of images of people could be skewed towards attractive looking researchers. Or it could be skewed towards ordinary looking celebrities. So, and we labeled them wrong, don't worry about that. So we train a neural network for smile detection, and we are able to infer these global properties from the neural network itself. We do not have access to the target data set, but we have access to the neural network, and we can infer this from the neural network itself. So let's see how this attack is carried out in practice. The key point to note here is that models trained on similar datasets using similar training methods should represent similar functions. And we use a machine learning model to predict whether the target classifier was trained on a dataset having the property P or not, which is P bar. So we use a machine learning model to classify a machine learning model. This is sort of confusing, so we've named this machine learning model a meta-classifier, the one that takes as input a classifier that is named the meta-classifier. And it basically takes as input the target classifier and predicts a label P or not P, depending on whether the dataset the target classifier was trained on exhibited the property P or not. Okay, so now the attacker has to obtain this meta-classifier. In order to obtain this meta-classifier, he has to obtain a training set for the meta-classifier. Now, a training set for the meta-classifier is a bunch of shadow classifiers. Now, these shadow classifiers are basically proxy classifiers that the attacker trains to mimic the target classifiers. So if the target classifier was a smile prediction neural network, the attacker trains a bunch of smile prediction neural networks by himself. And to train these shadow classifiers, the attacker needs shadow training sets. So the attacker has to obtain a set of shadow training sets. Let's say he obtains k shadow training sets, ideally half of them exhibiting the property P and half of them not exhibiting the property P. And he trains a bunch of shadow classifiers from them, from which he uses the features with the label P or not P to train the meta-classifier. So let's see. So first of all, let's talk about feature extraction here. So the original attack evaluated this attack on HMMs and SVMs, which are hidden Markov models or support vector machines, and they were able to use the parameters as the feature vector. For neural network, the parameters are the weights and biases. So one could fathom just using just flattening out the neural network, concatenating all the weights and biases into a very huge feature vector, and where each dimension is basically either the bias of a particular node or the weight connecting two different nodes. And this is our baseline. So when I say this is our baseline, it clearly does not do very well. Simple vector representations do not work well with neural networks. So you can see these three, sorry about that, but you can see these three different tasks. One of them will be clear soon, but all for smile prediction, which is what we were talking about previously. And there are three different properties that we tried to infer. One is a higher proportion of attractive faces, which is the case study I was talking about. One is a high proportion of older faces. One is a high proportion of males versus females. And you see that the baseline performs close to 70% in the first case, close to 80% in the other two. And you might think that these accuracies are fine, but I can tell you and I can assure you, and I can show you that we can do much, much better than this. So why do simple vector representations, why don't they perform as well with neural networks? So let's take a look at these two neural networks, and I'll pause just for a few seconds to let you see what the difference between the two of them is. So essentially what I've done is I've just swapped the blue node and the green node, which is labeled 1 and 2, with their weights intact. So for example, the weight connecting the green node to the next layer, which is valued at 1, is also valued 1 in the other neural network F2. So the weights are intact. The biases are also intact, although they're not shown in this. The biases are also intact. What I've done is only swapped around a few nodes. And this should not affect the neural network at all. In fact, they should be the exact same function. But let's look at the vector representation. So you can see that the vector representation, when flattened out, looks kind of different. And this makes it very tough for the meta-classifier to be able to classify, to be able to recognize these neural networks. So F1 and F2 represent the exact same function, but have very different flattened representations. And this makes the job of the meta-classifier very difficult. So we want to address this. We call these neural networks permutation equivalents. It's there in the paper. And I also want to note one point here. There are 3 nodes here. So there are 3 factorial permutations that you can obtain. If there were n nodes, you could obtain n factorial permutations. If there were k layers with n nodes each, you would have n factorial to the power k. That's just a tiny bit of math, but that tells you how many permutation equivalents there are in total, which is a large number. So how do we address this? So to reiterate, we basically want to remove the effects of permutation. And as you see in the diagram, we want different orderings of nodes within the same layer to have the same output when passed through the meta-classifier. So there are 2 ideas that we came up with. The first idea is that you make sure that the meta-classifier sees only one ordering. You sort the nodes. So how would you go about sorting the nodes? So you define a metric to rank the node within a layer. For our purpose, we used the magnitude of the sum of weights. You can use any metric, and we were able, and then you perform a node permutation on the layer to obtain the sorted order based on that metric. And if you do this for all layers, all permutation, and if you do this for all layers, all permutation equivalents will have the same ordering. So let's see how this does in practice. So these are the same three problems. There is attractiveness bias, there's age bias and gender bias, and I've plotted the accuracy on the y-axis. Starting from 50%, if you do worse than 50%, you're better off predicting what you weren't going to predict. So 50% is the baseline here. And you can see that there is a trend. We do perform much better, but we can perform even better than this. So let's talk about another idea. Now, sorting the nodes is a sort of, it's a pre-processing step where you basically make the job easier for the meta-classifier. What if the meta-classifier was smart enough to be able to disregard the effects of permutations or ordering? If the meta-classifier was able to work on a sort of unordered representation. So if we were able to do that, then we could simply use an unordered representation. And what is an unordered representation? An unordered set. So you can think of each hidden layer not as a list of nodes, but as an unordered set of nodes. And each node itself is simply its weights, is described by its weights and bias. So you now have an unordered set of weights and biases. So let's see how we can construct a meta-classifier to be able to work on an unordered set. Now, in the set-based representation approach, what we do is we flatten out the neural network. Now, this is not the same as flattening out the entire neural network into a single feature vector. We flatten out each node separately into its weights and bias, and we now have an unordered set of weights and biases, as we talked about. And we do this for all hidden layers. You can ignore the N1 being concatenated to the weights and bias of the second hidden layer. We can talk about it in the questions, or you can look that up in the paper. It's just a slight optimization that helps improve our accuracy. So after you obtain this unordered sets of weights and biases, you pass them through a node processing function to obtain a node representation. So this is a simple function that looks at the weights and bias of a single node and obtains a node representation out of that. So for example, if the first layer has 10 nodes, phi1, which is the node processing function of the first hidden layer, would be called 10 times to obtain 10 different node representations. And similarly, phi2 would be called as many times as there are nodes in the second hidden layer. And now we have an unordered set of node representations, but we eventually want a single prediction from this. We want to classify whether the dataset follows P or not P. Coming back to the problem. So we want to summarize these node representations somehow without inducing some sort of effect of ordering. So clearly we cannot sort of concatenate them and then pass them through a neural network that would order them again. So instead of that, what we do is we do a layer summation. A layer summation is basically a summation of all the node representations within a single layer to obtain a layer representation. And layers are ordered. There is no, you cannot permute layers without changing the neural network. So you can just concatenate the layer representations to obtain a classifier representation, pass that through a prediction function to obtain the label. Now let's see how well this does. And one more note is that this architecture is basically inspired from the deep sets paper. And there are some changes. For example, the deep sets paper wasn't meant to work on neural networks as input. And there are some optimizations that we've done as well. So we basically solve the task. This is the same task as earlier. We are very close to basic. I mean, apart from the attractiveness bias problem, we get really high results, close to 100% in both age bias and gender bias. And that's why I said we can do much better. So inferring whether there's a bias in the data set is concerning, but let's look at a more scarier problem. So here is a Bitcoin mining detector, which looks at hardware performance counter values for different applications on a desktop and predicts if Bitcoin mining is running on that desktop or not. What if I told you that looking at just this Bitcoin mining detector, I could predict if your system was patched for Spectre and Meltdown or not? Now that's something that is pretty sensitive and possibly opens doors for more attacks. So let's look at how well and this is also a tougher problem because the patch itself affects your counter values in very intricate ways. There are machine learning classifiers that figure out the patch, whether there's a patch or not, just looking at the counters. We instead are looking at the classifier that was trained on those counters to infer whether there's a patch or not. So that's interesting. And let's look at the results. So you see that clearly this is a tougher problem. So the set base doesn't go to as high accuracy values as it did before, but it still is pretty high, and you can still see the trend. Sorting does better than baseline, and set base does better than sorting. And set base reaches almost close to 90%. I think it was 87%. So we also evaluated this on different data sets and other properties. There's a US Census income dataset which has on which we performed inferring income distribution, whether the dataset was biased towards more or less high income data points. There was gender distribution bias. There was racial distribution effects. So in one property we had whites in the dataset. In the other we removed whites entirely, and we were able to predict if there were whites or not in the dataset. Then there's the MNIST dataset, which is basically the US Census income dataset, I should have mentioned this, is basically a dataset of demographics where each person, so basically each data point is a person, and the label is whether or not that person earns more than $50,000 or not. And the attributes are basically the demographics, age, gender, etc. The MNIST is a data set of images of digits 0 to 9. And we were able to infer whether or not the digit recognizer was trained on noisy images or clean images. And this is a slightly different attack in the sense that this is also a sort of environment. You can think of it as trying to infer some competitive advantage that a particular model producer might have used, training on noisy images to make more robust models. We also inferred some other dataset distributions for the Celebi dataset, but I've not shown them here. You can see those in the paper. So this summarizes the attack effectiveness by large. So there's the income bias. You can see the same trend in all 4 of the different experiments. Some experiments are inherently simpler than the others. Some are tougher than the others. But what I want to capture here is basically that you can see the same trend here. And there are some cases where the baseline performs really high, but you can see that mostly the set base retains an accuracy of greater than 80%, which is pretty good. So with that, I would like to conclude my talk, and I'd like to mention 3 major points. So we've identified permutation equivalence as one of the major factors that makes meta-classification difficult for neural networks. We've developed 2 improved approaches addressing permutation equivalence, which allow meta-classifiers to better analyze neural networks, that is the sorted representation and the set-based approach. And we've evaluated and successfully demonstrated attacks which could leak sensitive or confidential information. So with that, I open to questions.
Very great presentation. Thank you.
Thank you.
If you go back to your slide 36, I'm just curious how sensitive your classification is to the proportion of biases. You have racial distribution where you completely eliminated
Yes.
whites. But what if you include 10% of the whites or 20%? What is the threshold and how sensitive? Have you run the test?
So I will admit that I have not tested that out very extensively, but I would like to point out that you can see that in the racial bias experiment, these are the results. You can see that baseline performs slightly well. The set base retains its accuracy regardless of the experiment on the UCI dataset. It's pretty good regardless of which experiment we look at. But in the racial bias case, the baseline also performs very well. So I guess that could point to the fact that since we remove whites entirely, so that was a simpler problem to solve, and that's why the baseline did very well. That still doesn't take away the fact that set base performs very well in very difficult tasks as well, such as the other tasks, the MNIST task or the hardware performance counter, the Bitcoin mining task.
Thank you.
Thank you.
Thanks. So Yang Zhang from CISPA Germany. So very nice work. So I'm wondering, so whether, because your attack is white box attack, yeah?
Yes.
So whether it's possible to actually generate the attack to a black box.
That's an awesome question, and I happen to have a slide for that.
This is unpublished yet.
So I'll just take a tiny bit of time for this. We tried out a black box. So first of all, there are existing techniques to convert a black box to a white box, but we have not tested on that. So one could try using that out. I think that's a possible use case. And another thing that we tried was, instead of predicting on the model parameters, we look at the so say you have a model trained on a data set of property P. Now you would expect that it performs poorly on a testing data set of property P bar. So just looking at the accuracy, its test accuracy on a data set of property P versus its test accuracy on a data set of property P bar, you would expect to have some sort of differentiation. And that's what we did. We used a meta-classifier only on the label of basically these are 2 points. This is a 2-dimensional classification. The input is accuracy on test data set P and accuracy on test data set P bar. And this is what we got. So here is the, we've plotted here just the accuracy. Okay, the y-axis is the accuracy on clean MNIST images. The x-axis is the accuracy on noisy MNIST images. The crosses are classifiers trained on clean MNIST images. And the red dots are classifiers trained on noisy MNIST images. It's sort of complex. I mean, just to simplify this, you ideally want to see here that the red dots, which are classifiers trained on noisy MNIST, should be lower and doing better for accuracy on noisy MNIST images. But you don't see that. You don't see any distinction between the two types of classifiers. And that's what we saw in our results as well. This is the results. So we used a KNN as the meta-classifier since it was only looking at 2-dimensional points. And it does not do, I mean, it does fine. It sometimes beats the baseline, it sometimes does not, but it's not stable. So it's not as good. And you would expect that as well because your white box, you have more data to analyze. Yeah.
Kevin from University of Chicago. Thank you so much. It's a very nice talk. I just want to clarify that if I understand it correctly, so each your training sample is a neural network, right?
Yes.
And how did you generate your training data set? So you will have a bunch of like neural networks with same architectures but different property labels, right?
Yes. So 2 different property labels. So for example, for the evaluations, we trained 2048 4096 shadow classifiers, 2048 of one type of property P, 2048 of P bar. We've shown evaluation which allows you to do it for a lesser number of, we can still do it pretty effectively for say 512 and 512, but then yes, you need to train on classifiers.
A quick follow-up. So can you apply the similar methodology to models with different architecture?
That's a great question. So no, we've not tried it. And yes, I think there are extensions to this that can accommodate for different architectures. So for example, if you just limit your difference in architecture to different number of nodes in the same number of hidden layers, but different number of nodes in the same hidden layer, then I think the set-based approach will still work, but you'll have to evaluate it, of course. Otherwise, you can also go for a graph-based representation. So we tried a graph-based representation, but it was very unstable. But I think more work can be done on it to make that happen.
All right, thanks.
Yeah.
Tudor Dimitras, the University of Maryland, great work. Congratulations. I just wonder, so here you were looking for specific biases, right?
Yes.
So you knew that you were looking for if the data set is gender biased. So
yes.
Could you infer from the model that there might be a bias if you didn't know exactly what to look for?
So I would say that you need to know what you're looking for example, a gender bias, but you need not necessarily say that, again, we've not evaluated this very extensively. I've done some work on this, but then it's not extensive enough. So you can, for example, say that, okay, there might be a gender bias in this data set. Let me see how much it could be.
I guess more specifically, I'm wondering, so there's all these Trojaning attacks. Could you infer that, the network might have a Trojan?
Okay, so I could maybe, but the Trojaning attack affects the neural network itself. I don't think it has to do anything with the data set. So the good thing about this work that I feel happy about is I think this is a generic sort of meta-classification. So you are able to analyze neural networks better. So I think it could be extended in that direction, yes. But that's not exactly the work that we're presenting today. But yes, I do think that it could possibly be extended in that direction. Yeah.
Okay, let's thank the speaker again.